In this video, we're going to take a look at how we can use the dot product that we've just learned about to calculate angles and work with angles between vectors. A nice thing for us to be able to do would be to take two vectors like u and v as I've drawn here, and to calculate the angle between them. Now, if we remember back to our discussion about adding and subtracting vectors, when we have two vectors drawn like this, we actually have a triangle as well, because it's pretty straightforward to add in the third side of the triangle, which here would be v minus u. Remember, when we're doing a difference, the positive thing points to the positive thing, so that's v minus u, not u minus v. So if I add in the line v minus u there, we've formed ourselves a triangle. And remember, we also know what the lengths of these things are, because we've figured out to calculate length, we just need to take this length operation, which is the square root of the sum of the squares of the components. So the length of this side is v minus u, with taking the length. So what we have geometrically is a triangle where we know the lengths of three of the sides, and we want to find the angle, or one of the angles. So if you think back to high school, you probably came across in trigonometry this rule called the cosine rule. And that's the rule that links together three sides of a triangle with one of the angles. And we've pictured it over on the right here, but we've got three sides. C is the one that is opposite the angle we're interested in. And it's a formula that looks quite a lot like Pythagoras with an extra term involving a cosine added on there. So let's see if we can use it for this picture we've got here. So our C side is going to be the length of v minus u. So if we were to just essentially write down directly how this applies to our picture, we have the length of v minus u, now it's c squared, so it should be squared, is equal to the length of a squared. Now length of a, so u is going to be our a, so it's going to be the length of u squared, and b is going to be the length of v, so the term b squared will be the length of v squared, and then I have a minus 2a, which is length of u, b, which is length of v, times cosine of theta. Okay, so what are we going to do with this? At the moment, we could just rearrange this formula for cosine theta and we'd be done, but it's a little bit messy, and it turns out that with a bit of algebraic manipulation, we can make this expression a whole lot friendlier to work with. So we're going to use this key little fact, or little piece of information, that the length of a vector squared is equal to the dot product of the vector with itself. And we're going to use this everywhere we've got a length squared to see if this is going to simplify our problem at all. So I'm going to replace my length of v minus u squared with a v minus u dot v minus u. I'm going to replace my length of u squared with a u dot u. I'm going to replace my length of v squared with v dot v. And then I'm going to leave the rest of it alone because it doesn't look like there's any nice simplification we can do there just yet. Okay, this is getting a little bit cramped, so I'm going to use the full width from here on. Now, when we're working with the dot product, we're allowed to expand out parentheses just in the same kind of way that you normally would, except that all the multiplications are dot products. So on the left, this becomes v dot v, so I'm expanding out our parentheses in the normal way, so v dot v, we're going to have that, we're going to have a minus u dot v, then we're going to have a minus, what have I got, a plus u dot u, because it's a minus minus, and I'm going to have a minus v dot u on the left there, and on the right I've still got my u dot u and my v dot v, and then I've got the minus 2 length u, length v, cosine theta. Okay, so far so good. Now if we just take a little bit of a careful look, we can see that we actually have some terms that are the same on both sides. So I've got a u dot u here that I can just cancel off, and I've got a v dot v that I can just cancel off. And another property of dot products is that u dot v and v dot u are the same thing. So this simplifies down to negative 2 u dot v is equal to negative 2 length u, length v, cosine theta. Final step is we have a factor of negative 2 on both sides that we can just divide through by. So that is also equivalent to u dot v is equal to length of u, length of v, cosine theta. Okay, so that's quite nice. So what we've actually managed to come up with here is a rule. U dot v is length of u, length of v, cosine theta, that expresses the dot product as a function of the length of the two vectors and the angle between them. If we want to actually find the angle, we just rearrange it to have cos theta is u dot v over the length of u, the length of v, and then we calculate that and take the inverse cosine to get our answer in radians. Before we work through a problem where we find the angle between two vectors, we're just going to also define quickly the concept of two vectors being orthogonal. So if I've got two vectors u and v, we say that they're orthogonal if their dot product is 0. Now, it'd be good to have some kind of idea of what that means, so we can get some insight into this by looking at the formula that we just derived before. So I've got this formula, u dot v is length of u, length of v, cosine theta. Now if we assume that our vectors are not 0, so they have some kind of positive length, then the 0 component of the dot product can only be 0 if cosine theta, if this cosine theta term here is 0. Because normally, length of u is not going to be 0, nor is length of v, and that means that for these vectors to be orthogonal, cosine of theta must be 0. Now let me switch to a less colorblind, unfriendly color. So if they're orthogonal, it means that this cosine is 0. Now the angle between two vectors can only really go between 0 and pi radians, or 180 degrees. So if we look at our graph of where cosine is 0, we remember that cosine happens to be 0 exactly when theta is equal to pi over 2 radians. So just also remember pi over 2 radians equals 90 degrees. So the meaning that we are to understand from this orthogonality thing is two vectors are orthogonal if their dot product is 0, which means that cosine theta must be 0, which means that the vectors must be at 90 degrees to each other. Okay, so the geometric understanding of orthogonality is that the two vectors lie at right angles. So for example, if I chose to like this, let's just say for sake of argument, A is 1, 2, and B is, let's think of something at right angles to that, is going to be negative 4 and 2. Okay, you can sketch these out yourself. In fact, I encourage you to do that. But if we were to calculate their dot product, I'll have A dot B is equal to 1 times negative 4 plus 2 times 2, which equals negative 4 plus 4, which equals 0. Okay, so these two vectors are indeed at 90 degrees, and it shows up in this dot product. So if our dot product is 0, it means that we know that our vectors are at right angles, which is a really interesting property of the dot product. So the last thing we're going to do is we're going to actually solve a problem that looks a little bit tricky. And I suspect going into this, it would have been a little bit of a challenge to try and figure out how to do this. So the problem we're faced with is we've got a cube. So I've tried to sketch a cube here, and we're interested in finding the angle between a diagonal that goes up the center of the cube, like this top yellow line here, and the face, the bottom face of the cube. So what I've done is I've dropped this diagonal down onto the bottom, and I've sketched in the angle that we want. Okay, now this is a little bit tricky, but actually it's not so bad once we start thinking of it in terms of vectors. So the first thing I'm going to do is I'm going to stick in some coordinate axes so that we can define some actual vectors here. It's not very good, that'll do the trick. And then we'll have also a z-axis up here. And just to make our lives easy, we'll label this 1, 1, and 1. So now we can actually represent these two yellow lines here as vectors in this coordinate space. So I'll call this one A, and I'll call this one up here B. So just by reading off the coordinates, I can see that A is equal to, well, let's see, the x component is 1, the y component is 1, and the z component is 0. And for B, the x component, y component, and z components are all 1. Okay, so to find the angle between them, this is now just a case of using our formula. So from the previous slides, we had that cosine theta is equal to A dot B over the length of A times the length of B. Okay, so what we'll do is we'll just figure out what all those quantities are off to one side just to keep it tidy. So A dot B is equal to 1 times 1 plus 1 times 1 plus 1 times 0, which equals 2. The length of A is the square root of 1 squared plus 1 squared plus 0 squared, which equals root 2. And similarly, the length of B is equal to root 3. So the last thing we want to do is to plug all this into our calculator or into our computer or however we're going to do it, and we'll get cosine theta is equal to A dot B, which we said was 2, over root 2 root 3. And if we like, we could notice that 2 divided by root 2 is root 2, so it also equals root 2 over root 3. And so theta is equal to the inverse cosine of root 2 on root 3, which, if you plug it into a calculator and you make sure you're in radians mode, will get you approximately 0.615. I'm just going to state that to 3 significant figures. Now, it's all very well stating things in radians, but it's often better to state answers at the final answer in degrees so that it's easy for a person to understand. So I take my 0.615, I multiply it by pi over 180 to get, 180 over pi to get degrees, and I get approximately 35.3 degrees. And looking at our picture, that seems reasonable. It seems like it should be less than 45, and that seems like an answer that makes sense. So we'll stop there.